Anyone tell me how do you define electric potential?
Electric field into distance. Electric field into distance.
You know, remember we defined potential in gravitation also?
Yeah.
Yes.
So they have to bring a charge from infinity.
Here we defined potential in terms of. See, remember, whenever we do some work against the conservative, you remember conservative forces? What are conservative forces?
Forces
Path followed does not matter.
Huh?
Path followed does
One thing can
be stored.
can be stored. Can friction be stored? Work done against the friction can be stored?
No.
See, if I slide this, there is friction, right? Now, is this friction stored or dissipated?
Dissipated.
This is dissipated in the form of sound, heat, right? These are non-conservative forces. These are non-conservative forces. Conservative forces are those forces. If I do work against those forces, if I do some work against those forces, the work done will be stored in the form of potential energy. Such forces we call as conservative forces. And remember, I told you in 11th grade that all central forces are conservative in nature. Is gravitation central force? Acts from one body to another body, center of one body, center of mass, one body to center of mass of another body, right? Earth attracts me towards its center, right? I attract also Earth towards my center of mass. Do you understand? So it's a central force connecting two centers. And remember, I told you all central forces are conservative in nature. Conservative in nature. I can conserve those forces. I can conserve those forces. I can store those forces. I can store those forces if I do work against those forces in the form of potential energy. So can you give me an example? Yes. For example, this is a bottle. Okay, it carries some mass. Why is the force acting? Downwards, right? Towards the center of Earth. Clear? Now I will do some work against this force. Okay, force is downwards. I will do some work against this force. For example, the Earth attracts this bottle with a force of 10 newtons. How much? 10 newtons. If I exactly apply 10 newtons, how much? 10 newtons. And move it infinitely slowly, slowly, and bring it to some height, h. Bring it to some height, h. Did I do some work against the gravity? Yes. Why did this work go? Why did this work go? Work must go somewhere, right? According to conservation of mass and energy, and conservation of work done must go somewhere. It must go somewhere. Either it must dissipate, or it must go in terms of heat, or it must go somewhere. Yes or no? If water flows from a dam, right, then water has some potential energy, right? Then potential energy gets converted into kinetic energy. Hello, please pay attention. Gets converted into kinetic energy, and that kinetic energy is involved in doing some work, rotating the blades, right, of the motor. And that blade, so basically potential is getting converted into kinetic into work done is converted into electrical energy. Is it getting dissipated? Is it getting lost somewhere? No. It might get transformed heat also, sound also, but it will not get dissipated. Simply vanish. It will not be. Okay. Am I doing some work? Yes. Against gravity. Now, why is this work on?
Still there, stored.
It's still there. It's stored in the form of potential energy. In the form of potential energy. Now, once I release this object, this potential energy gets converted into kinetic energy. Yes or no? Yes. But the sum will remain always constant. Remember? For example, the total sum is 50 joules. Total sum is 100 joules. If here it has potential of 100 joules, it's only due to potential. Yes. Now once I release it, this gets converted into kinetic energy. And finally, when it comes to the zero potential, this whole potential energy gets converted into kinetic energy. But still, the sum will remain 100 joules. In between, it will remain 50-50. But the sum will totally remain 100. Is it clear? So we did some work against the gravity, which is conservative force, and we found out that there is some potential. Or spring, okay? Spring is the best example of spring force is conservative also. And we do some work against the spring force, against the compress the spring. Okay, now this energy is stored in the form of spring potential energy. Okay, once I release it, it will get converted into kinetic energy. Yes or no? Similarly, this also will drop this potential get converted into kinetic energy. Thus, we can see that this basically the force work done against this conservative force is getting stored in the form of potential energy. Such forces we call as conservative forces, and the work done against them, okay, force is downwards, and doing the work against this force is getting stored into potential energy. Do you understand? Similarly, our electrostatic force is also conservative in nature. It can also conserve energy in the form of potential. It has some potential to do work. Is magnetic force conservative? That's also conservative. You will see that. Okay. Did you understand? Is it clear? Now look. I will explain potential. There I explained potential as I took a test mass. And that test mass I moved from infinity to some point inside gravitational field. The work done which I did for that point mass to bring it from infinity to some point inside gravitational field was stored in the form of potential energy. And at that point I could define potential. Remember? Is it clear? Similarly, here also we'll do the same thing. There we took the test mass, here we take the test charge. Otherwise the things will remain same. Do you understand? The basic difference between gravitational force and electrostatic force is that the gravitational force is always attractive in nature, but electrostatic force can be attractive as well as repulsive. Okay. Now, in order to define the electric potential mathematically, what I will do is I will take a system of charges. There I took system of mass. Remember? Here I will take system of charge. What does it mean? It contains some amount of charge. This body, anything. Okay. Clear? Now, what I will do is this system of charge will have some field around it, right? Will have some field around it. Once it has some field around it, I will take a test mass. I will take a test mass. Sorry, test charge. Now I will not take test mass. I will take test charge, and I will take unit positive. Unit positive. I will define it also as unit. Unit means 1 unit. Okay, unit positive. Very small magnitude. Okay, small. Like we took small magnitude there. Here also we take small magnitude in order to just define this. Clear? Fine. Unit positive test charge. Unit positive test charge. Q0. Okay. Now I will do some work. Now look here. Forget about this. Okay. Forget about this first. Tell me, if this is positive charge, this is also system of positive charge. System of positive charge. Just for the definition purpose, I will put positive over. Okay. This is also positive. This is also positive test charge. Tell me, in which direction will be the force? Repulsive, right? It will be repulsive and it will be opposite. Clear? What kind of force will be that? Electrostatic force, right or not? So it will be electric force or electrostatic force. Now I need to do work against this electrostatic force. Like I did the work against gravitational force, right? Gravitational force was downwards. I did some work against this force, brought it to some height h. Clear? Brought it to some height h. Here I defined its potential. Similarly, what I will do is I will also bring this positive test charge from infinity, from some point infinity, to some point inside its field. Let's suppose that point is P. That point is P. I will move this. How will I move this? I will apply some external force. Will I? Yes. Against this electrostatic force. How much force should I apply external? Tell me. Can anyone tell me? How much external force should I? If this is 10 newtons, for example, how much should this be?
More than 10 Newton.
Obviously, it must be more than. This our mind tells us. It must be more than. If it's 10, it must be 10.1 something. But then there's one problem. This body will start to accelerate. Why? Why it will start to accelerate? Because whenever there is force, net force, the body starts to accelerate. Yes or no? Whenever there is force, there will be acceleration also. But net force will be 0. If its net force is 0, either the body will stay at static equilibrium or the body will start moving with a uniform motion. That way I will move this. Otherwise, acceleration will change its kinetic energy as well. Here, for the definition purpose, whatever force, like electrical force is there, the same amount of force I will apply external and move it infinitely slowly to point P.
But if it's at rest and you apply force with
This is just mathematical interpretation. Okay. Otherwise, we cannot do. Practically, we cannot do this thing. Huh? If I place exactly this is at rest, I placed 10 Newton force. I placed it at rest. 10 Newton for 10 Newton. Net force is 0. It's at rest. If it was a uniform motion, it can also be uniform motion also. Yes, net force still be 0. Clear? But now if there is net force, it will accelerate. Will it? Yes or no? Clear? Whenever there is net force, the body will accelerate. So here I am assuming that I have no net force. So I will apply exactly the same force and move infinitely slowly to point P. But whatever work I have done, why will that work go?
Stored as potential.
That's work done will be stored as potential energy. Is it clear? So can I define potential at P also now? Yes. For example, now I move this particle r distance away. Okay. I move the displacement of r from here to here. R. Can I write the work done?
Force.
Work done. Tell me. Work done by. First tell me. Work done by external force. Force
Into displacement.
Force into displacement. Clear? Force into displacement. How do you define work? F into integration of F dx. Clear? Is it clear? Yes or no? How much force should I apply?
Equal.
Exactly same force. But look here. If I do the work by external force, the work done will be positive. Because F and R, the angle between them is 0. Is it clear? Work done by external force and the work done by electrostatic force, they will be opposite. They will be negative. Do you understand? Because here the force is acting this way and the displacement is to the left. Cos of 180 degree. So the work done is F dot S. Yes or no? Clear? So here the work done will be negative and here the work done will be positive. So I can say one thing: the work done by the external force will be negative of work done by electrostatic force. Yes or no?
Yes.
Clear? How do I define potential? Okay, potential type, not potential energy. Now this work done, whatever work I did, again is this electrostatic force will be stored at potential energy. If I find the value of this work done, I will get potential energy. But what is potential? Potential I define as, potential at any point P I define as work done by this external force, to bring the charge from infinity, right, to some point P. Is it clear? Work done by external force to bring this positive test charge from infinity to point P. Per unit test charge. This is my potential. This is how I define potential. Is it clear? Work done by external force from moving the positive test charge from infinity to some point P per unit test charge. I define potential at that point. But how did I move this? Very slowly. You have to remember. Is it clear? Or can I say negative of work done by electrostatic force or electric force from bringing a positive test charge from infinity to some point P? Because it will be negative. Do you understand? Clear? How it will be negative? You know that. F dot S. Clear? If the angle between F and S is 180 degree, force is acting this way, displacement is this way, the angle is
180.
180. Cos of 180 is
Minus
minus 1. So minus work done. Okay. What if the force is in the same direction? Then it will be F dot S cos of 0. Is it clear? That's how the external force is negative of the electrostatic work done. Do you understand? Yes or no? Clear? This is clear to you? Okay. Now, so can I write this as the work done by electrostatic force from bringing a positive test charge from infinity to some point P divided by Q naught. These are the two definitions. These are the two definitions
For potential.
for the potential. Okay. Work done. Tell me what is the definition? Work done by external force, right? Work done by external force to bring the positive test charge, positive test charge from infinity to some point P inside the electric field. Yes or no? Per unit test charge. Per unit test charge is defined as potential at P. Is it clear? Or how can I define? Can you tell me? How will I define? Electric force. Very good. Negative of work done now, right? Negative of work done by electric force to bring the same positive test charge from infinity to some point P inside the field. Is it clear? Yes or no? Yes or no? Clear? Done? Now, changing the limits. If I want, I don't like this negative sign. I want to remove this negative sign. I will just change the limit P to infinity. P to infinity. Just for all these things I am doing just to, get mathematical idea about this, okay? What it basically is. Can I say P to infinity now just to remove this sign? Remove the negative sign. All these three definitions are valid? Yes, they are valid. Is it clear? Is it clear? Why I did this? Because I know electrostatic force. I don't know external force. I know the value, how I calculate the electrostatic force. Okay. Now this is the system of charge. This is the system of charge. It will have some field around it. Will it have some field around it? Let's suppose that field is E. That field is E. That field E here, is it constant or variable? Variable, right? There will be field lines that will not be uniform definitely. Is it clear? Yes or no? Yes. Can I write this electric force as Q naught into field at this point? Can I write Q naught into field at this point? Do you understand? Is it clear?
Yes.
Is it clear? Can I write this? Now, in order to calculate the work done, first I will, can I write the work done is nothing but integration of F dot dr. Do you understand? What is this force now? This force will be my electric force. Force will be my electric force. Okay. Now I have changed the definition from P to infinity. Do you understand? I will change the definition from P to infinity. So that means I will put the lower limit as P and upper limit as infinity. That's how I will get the work done. That's how I will get the work done. See, I removed this minus sign first, right? Now I change the limits, the sign changed. Okay, the sign of this integration will change. Yes or no? So I change the limits from P to infinity. Now I will integrate it and get the work done. Now what will be this work done? Work done by external force also and work done by electric force also, both of them. But just the signs will be opposite. Then the signs will be opposite. External work done will be negative work done and the electrostatic work done will be positive work done. Sorry, electrostatic force will be negative work done and this will be positive work done. Do you understand? Clear? This is just for is it clear? Yes or no? Now tell me, what is my Fe, electric force? Q naught, yes, multiplied by the field at that point. Yes or no? Q naught into E. Now tell me, is this E variable or is it constant?
Variable.
It's variable. Okay. Can I take Q naught out of the constant? Can I take Q naught out of the integration?
Yes.
So once I take Q naught out of the integration, I will get Q naught into integration of P to infinity, right? E dot dr. E dot dr. Whatever value we will get here, will that be the value of potential energy to get? Potential energy. Work done is potential. Work done per unit charge is potential. Remember.
Okay. This is for potential energy.
This is for this work done. Whatever work we do will be stored in the form of potential energy. This whole thing will be potential energy. Potential. Later on we will define this again. Okay. But for now I am just giving an idea. Okay. But according to the definition, it's not work done. It's work done per unit test charge. Do you understand? So can I put the value of work done here? Yes or no? In order to define potential, in order to get potential? Okay, what is the potential now? Can I write potential will be nothing but, now this I know, what is it? Q naught into integration of E dot dr, okay, from P to infinity divided by Q naught. Divided by Q naught. Is it clear? Is it clear? Now this Q naught and Q naught gets cancelled. And we get potential as integration of E dot dr. Now this is very important. This is very important. From P to infinity. From P to you understand everything. Once I define potential difference, everything. Now this, you remember E dot ds? Wait, remember E dot ds? E dot ds was surface integral. Remember? Surface integral of electric field intensity. Now this is potential. How it is defined as? It's line integral. It's defined as line integral. This R is defined as, this is basically line. So S, if it was S, remember? If it was S integration of E dot S, what is it? Flux. Flux. Remember? Surface integral of E dot ds. If we put 0 here, means closed loop. Remember? Closed loop. Now, if I write E dot dl or dr, basically its length. This is not length, this is area. That's why we call it as surface integral. We call it as surface integral. And this we call as line integral. This we call as line integral. So can I define potential is nothing but line integral of what? line integral of, tell me, electric field intensity or electric field or electric field strength. Okay, electric field. Okay. Line integral of electric field. This is my potential at point. Go. Understood? Clear? Yes or no?
Yes.
Now you write this. Wait, I'll make you write. First you write this. Definition. First you write definition. Electric potential. We did some work against gravity, stored at potential energy. Now, I did some work against electric force, right? Electrostatic force. The work is again stored in the form of potential energy. Here we defined gravitational potential per unit test mass, if you remember. We define gravitational potential as per unit test mass. Here we define it per unit test charge. Is potential scalar quantity or vector quantity?
Potential.
Potential or potential energy? Potential energy is scalar, it's energy. Yeah. Whatever potential. How do we define potential? Finally, what is the answer we got? Line integral of E dot dr. Dot product.
Scalar.
Answer will be scalar. Can anyone try its dimensional formula? Potential dimensional formula? Work done per unit test charge. Do you know work done? Dimensional formula? Do you know charge dimensional formula? No?
ML2 T minus 2C.
ML2 T minus 2 is work done, and this
AA, I think. A or
A into T is charge, right? Current is charge, right?
Charge. Oh.
Do not.
And
Let us write this. Finish this, please. Done this one? Good? You also write good? Should I write you that one or this one?
The one you wrote is fine.
Okay, so you draw the diagram first.
So can you show this thing, electric potential almost? 1 second. Should be at
So electric potential is defined as work done by external agent, right? To bring the positive test charge from infinity to some point P slowly, okay? Or it's defined as work done by electric force to bring it into positive test charge from point P to infinity. Because we have changed the limits. What did we change? The sign.
Yes.
Once we change the sign, we change the limits. Infinity to P, P to infinity. Just change the sign. I can say work done by electric force to bring yes or no?
Yes.
Understood? Now you see this. Because I defined electrostatic force from P to infinity. External force infinity to same or negative electrostatic force from infinity to P. Is it clear?
Yes.
Is it clear? Then I did nothing. I just found electrostatic force work done. Yes. F I know F dot dr simply. F I know Q into E. Dr. So Q dot I took out. E is not variable. That's why I didn't kept it integrated. Here. Now this is work done. This is basically stored in the form of potential energy. Stored in the form of potential. For this we'll put separate heading also. Okay. Now this potential energy, the potential is defined as this work done divided by point charge. I just divided this work done and found that potential at any point is defined as line integral of electric field. Line integral of electric field or electric field intensity. Clear? Things will be really clear to you. Once I go for different topics, everything will be clear to you. Clear? So maybe in beginning it will feel like it's very difficult to understand this, but you will get a whole idea about this potential. Okay? So clear with me. Did you write this?
No, the last one.
Hmm?
The diagram.
Diagram you will draw.
Okay, yeah, this is.
So for example, this is some field. Inside this field, how much work should I do? And that work done, again, same thing, man. See, I picked this bottle up against gravity. Here I didn't pick it up against gravity, I picked it against electrostatic. Now, look, I got this charge. I got this charge here. What if I release this charge now? Look here. What if I release this charge? Where will it go? This potential will get changed into anyway, it will run away. Whenever things running away, you remember it's stored in the form of potential. See here also, this bottle is running down. What is it doing? What is the bottle doing? Decreasing its potential. Decreasing its potential. Everybody wants to maintain minimum potential. Wants to maintain minimum potential. Practical example. For example, this is a ridge. This is a ridge. I'll keep a ball here. Where does this ball want to go? Will it want to stay in this thing, in this trench, or will it want to stay here? It wants to come down because it wants to maintain, but put some displacement to go down. It will want to maintain the minimum potential. Here it will have less gravity potential. Yes. Here it will have more gravity potential. Whether potential is anything, every body tends to maintain the minimum potential. Is it clear?
So next one.
That's why two charged bodies repel each other. Two positive charged bodies repel each other. Why? They want to maintain minimum potential. They want to maintain minimum potential. That's why two bodies attract each other. Here, gravitation, because they want to maintain minimum potential. This is the game of potential. This is the game of potential. Do you understand? Clear? Yes or no? Did you understand? Yes or no?
Yes.
This system of charge, any charge, it could have any charge. Any body having charge, this bottle having charge. Okay? The next I will define potential by a point charge. Potential by a point charge. But how do we write the potential by a point charge? Same concept, okay? Nothing new.
Next slide.
Next slide. Now you have to remember this. See, remember this. Potential, remember two things here. Potential is the work done by, again I will repeat, so that you will remember. Work done by electrostatic force to bring the positive test charge from P to infinity, not P infinity to P. For external it's infinity to P. For electrostatics it's P to infinity. One. Second thing, potential at any point is defined as line integral of electric field. Yes or no?
Yes.
These two things you remember. Line integral, not surface. What is surface integral of electric field? Flux. What is line integral of electric field? Potential. Not potential energy. Potential I'm defining. Okay. Later on different potential energy. Potential energy means nothing. This work done is basically potential energy. If I calculate, so for example, force is 10 Newton. Force is 10 Newton. Okay. I displacement upwards for 5 meters. For 5 meters. How much is the work done? Again. Force is 10 Newton. Apply external force, brought it up to 5 meters. How much is the work done? Minus 50. Minus we write because I did the work against gravity. So 50 joules of work is done. You know, that's how much potential energy? 50 joules. Same 50 joules. This work can be basically meant to do. Okay, yeah. Yes or no? Yes or no?
Yes.
Once I release it, once I in midway, yes, I lost also potential also. Yes or no?
Yes.
Work done still within 60. How much you got answer work done? 50. 50 joules. 25 will be work. 25 will be potential.
Middle here.
Here, kinetic will be 50. Potential will be 0. Both them will still yes or no? Similar thing here also. Clear? Yes. Whatever work I did to bring the charge is stored in the form of potential. If I did 60 joules work, that whole 60 joule work goes into potential energy. Then if I place it, it will go into kinetic also. And it will go in finite point, it will reach some infinity point, and we define and write this also. At infinity we define the potential as 0. Define as potential as 0. Look here, so see here what will happen. This is the system charge, this is the system of charge, okay? System of positive charge. Look here. This concept is very important. Here it has some potential, here it has some potential. It has potential, but kinetic is 0. It's at rest. Do you understand? Yes or no? Now once I release it, it crosses the boundary, goes to infinity. Here the potential will be 0. Kinetic will have some value. Here potential will have some value. The whole potential got converted into kinetic. Do you understand? Midway it will have some velocity. Once it has a velocity, it will have kinetic energy. Half m square. Yes or no? Yes. So here it will have potential also and kinetic also. But the sum of total energy will remain constant. If it was 60 joules of from the beginning I will tell you. I did 60 joules of work, brought it here. Why did the boiler go? Completely got converted into potential. So here how much potential? 60 joules. How much kinetic? 0. Now I release it. Somewhere in the middle. Are you here? For example, this is 40. How much will be this? Kinetic 20. Sum is again 60.
Some will always be 60.
Total energy always is uncertain. Okay. It goes to infinity. By infinity we have defined potential as 0. Potential is 0. Potential energy will be also 0. Do you understand? Is it clear? There will have 0 potential energy, but kinetic will be there. Now this particle will be having some velocity, maximum kinetic energy. It will never stop. Stop. With that constant. It's once I left it. See, mechanics behind this. See, listen. If someone understands this, please.
Yes.
Once I leave it. Velocity starts increasing until whole potential get incarnated into kinetic energy. For example, here the velocity of this particle is 3 3 meters per second. Tell me after this, will this 3 meters per second or some 43 meters per second? Okay, tell me, what is the velocity here? 0. It increases from continuously up to here. Can anyone tell me after this, what will it stop? What will happen to this?
It will either decrease or be consistent if there is no loss.
It will be same, right? Newton's
Third law. No.
first law.
First law. First law.
Body tends to remain this. Up to here, they were force. They were external forces. Here there is force, electrostatic. Here there is force. But when it went to infinity, there is no force now. There is no force now. No net force. No net force is there. The body will tend to remain in uniform motion or rest. So it will continue moving with 43 meters per second. Are you getting? Are you getting? Are you getting? Yes or no?
Yes.
Total mechanical energy conservation means total energy will remain constant. Remember total mechanical energy conservation I told you? Potential initial plus kinetic initial will be equal to potential final plus kinetic final.
Yes.
This is nothing but same total energy, this same thing. If you change U initial minus U final, K final minus K initial, it will be same. The potential is getting converted into kinetic into potential. So total sum remains constant. Finally, we got this something total energy conservation. If potential at initial, for example, potential at initial point is given. Potential at initial point is given. It's asked find the velocity of a particle. Find the velocity. Can you find? Let me tell you how. Kinetic initial is 0. Potential final is 0. 60 joules of potential energy. 60 joules of potential energy will be now kinetic energy. Will be now kinetic energy. So can I write you I is kF is equal to half mv square. If the mass of particle is given, for example, it's a proton. It's a proton. Can you calculate velocity? And can you calculate velocity?
Yes.
Done. Khatam. 2060 joules. N is given. 2 is given. V is calculated. Are you getting? Whole mechanics is involved. Whole mechanics is involved. Do you understand nothing? What I did? Total mechanical energy conservation. Work energy term. From work energy term we came to total mechanical energy conservation. But total mechanical energy conservation only valid for conservative forces. Or only valid for conservative forces. Yes or no?
Yes.
Do you remember now? Do you understand now? Do you understand this whole concept? If you want to write this also, now write these points also. Potential at infinity. Potential at infinity is assumed to be reference then 0. Okay? 0. Is it clear? Yes or no? So this is the first point. Second point. Potential is scalar. Potential is scalar quantity. So how do we know it's scalar quantity? Because it's dot product of E dot dr. It's dot product of E dot dr. So no problem, sir. It's dot product. Definitely it will be scalar quantity. Okay, sir. Understood. Understood. Sir, what about its dimensions? No problem. Dimensions are easy. Dimensions are very easy. Just we know V is W by Q naught. What is W? M1 L2 T minus 2. What is Q naught? Charge into, sorry, current into time. Current into time. So the answer will be M L2 T minus 3
A minus 1.
A minus 1. So this is the.
So could you show the previous slide?
Do you write this?
We'll write it just to check if I can surface line integral of
Line integral of electric. What is surface integral of electric? Understood? Clear? Need out? Need out in potential? No doubt in potential now? Now, let's derive one. This was just a system of charge just to define potential. Now what I will do is I will take a point charge. I will take a point charge. For that I will define potential. Like I define electric field for a point charge. What is it? KQ by R square. Yes or no? F by Q. Right? F by Q. Yes or no? Here also I will define. I will get the answer as KQ by R. AQ by R. Let's see. Okay? Do you write this?
Yes.
Done?
Done. So can you show the point?
Points?
Sure.
Write this also. Now we will remember potential is defined as work done by electrostatic force from moving a charge from P to infinity. Okay, so how did I make electric work done was negative? How did I make it positive?
From infinity to
Take
P
the limits.
to P
Take the limits. In integration, if you change the limits.
becomes opposite side.
I just defined it now from P to infinity. So why did you define? Because I knew how to calculate electric work done.
So how do you why does the sign change if you change the limits?
You check integration. If you change the limits, sign will change.
It's like a rule.
Huh? Will the sign change? Upper limit, lower limit, upper limit. Okay. Is it tough? little bit tough to absorb. Maybe with time you don't understand everything. But you understand that concept, very good concept.
Yes.
Huh? Done. Previous one? Is it done? We just define potential. Now we'll define potential due to a point charge. Potential due to a point charge. Right heading. Potential due to a point charge. Now we know potential is work done, again I'm repeating because I need this, work done by electric force to bring the charge from P to infinity, from some point to infinity, not infinity to point to infinity. Okay? Now we'll put lower limit as P, upper limit as infinity. Okay? P is lower limit, infinity as upper limit, because we are taking it from P to infinity for electric, just for the definition purpose. Because we know how to calculate work done by electric force, so we don't know how to calculate work done by external force. We know the formula of electric force. So no, Q into E, Q into E. Clear? I mean, yes or no?
Yes.
Okay, now, write the heading electric potential due to a point charge. Electric potential due to a point charge. Did you write? Then you have to remember that formula also. So, one formula, two formula. You have to remember. Okay? Concept also, not formula only, concept also. Everything I will make easy now. I will try to make it easy now for you. Because all this work, this hard work which we did, will be easy now. Okay? Because you have to remember this now. This thing. So do that point charge, point charge. Now I will take a point charge. Let's suppose this point charge is Q. This point charge is Q plus Q. Right, plus Q. Positive point charge plus Q. There I took system of charge. Here I took point charge plus Q. Now this we have some field around it. Yes or no? Okay. The same thing I will do. I will take a positive test charge, and I need to bring this some, let's suppose, distance r from this charge. Okay, and the distance of this charge is, let's suppose, x. How much? X. What will be the force acting on this? What will be the forces? The external force, electrostatic force. And how much will be this electrostatic force? Due to a point charge. Please tell me. Q into E or KQ1 Q2 by R square. You can write both ways also. You can write Q into E and field due to point charge. We know how much? KQ by R square. Nothing. Basically, we are writing the same Coulomb's law here. KQ naught. Tell me Q divided by
R square.
X square.
X square.
Yeah. Clear? Any doubt? Till here? Now I need to do work. Again, this electrostatic force to define potential. How would I define potential? Sir, no problem, sir. Now you know potential at any point P. Let's suppose this point is P. Is defined as the work done. So now I will not write external force. These things I will write simply electric force to bring the charge from P to infinity. Divided by Q naught. So I don't know how to calculate this. If it helps, no problem. Okay? No issues. Clear? How will I calculate work done? Work done is easy. Work done by electric force is easy. How? Integration of F dot dx. Clear? From now the point comes. From P to infinity. What is the lower limit? P. The position of P. And okay, what is the position P? Basically R. Yes or no? So basically R. The position of P is R. R to infinity. This is my work done. Sir, how to write F? No problem. F is KQ by Q1 Q2 by R square. Is it tough? Any doubt you have to ask me, please now. Should I continue? Okay. So I will write integration of R to infinity K Q naught Q divided by X square with respect to dx. K bar Q naught bar Q bar. Tell me, you are 12th grade students. Now expect the integration directly. 1 by X square integration is
X
Minus 1 by X.
So minus 2
plus 3.
X minus 3.
12th standard students integration.
1 by X square.
Wait,
Just 1 by X.
1 by X square. Huh?
Oh yeah, X
Minus 1 by X. Check it.
minus 1.
Everyone try. Integration of X is for 1 by X square. X is for minus 2 plus 1. Divided by minus 2 plus
X
1.
minus X raised to minus 2 by
Minus X is for minus 1, right?
Minus 1.
So 1 by minus 1 by X. Yes or no?
Minus 1.
Yes or no?
minus 1 by
Minus 1 by X. अरे भाई अगर ये नहीं आता तो मैं क्या करूँगा भाई? By X is for minus 2 plus 1 is minus X minus 1 by X. चलो ठीक है. तो हो सकता है इस इंटीग्रेशन कितना हो सकता है 1 by X. What is the limit? No limit. What is the lower limit? R. What is the upper limit? P. Oh sorry. Infinity. Done. Done? Get the answer here, both them. This will be basically potential energy which you are getting. Which will get the answer in potential energy. Tell me now. Fast, fast. Put the infinity limit. 1 minus of infinity, how much? Minus of infinity, how much? 0. Minus of minus, plus 1 by r. 1 by r we will get.
1 by yeah.
Is it tough?
No, sir.
So k q naught q by r. Is that the answer which you get? Again, 1 by x, put the upper limit. Infinity, 1 by infinity, 0. Minus of minus, 1 by r. Plus 1 by r. Is it tough? Is it tough?
No.
Such way? Is it tough? No. So what is the answer? K q naught q by r. This is my potential work done. This is my work done. Basically potential energy. Yes or no? The same work done is stored as potential energy. Yes or no? Yes or no? But is this potential? No. Potential is defined per unit test charge. So what I will do is k q naught q divided by r into q naught cancel. The potential at P is equal to now k q by r due to a point charge. Due to a point charge. What is field? What is field? Q by. Is it clear? 100% clear? 100% clear? So this is my potential defined at any point P. Any point P. Now put always this Q with sign. Sir, why with sign? Because the potential due to positive charge will be positive. And potential due to negative charge will be negative. And this potential can be 0 also. Okay, so potential can be positive, potential can be negative, potential can be 0.
How 0?
0 you will see. Okay? Infinity also potential 0. Yes or no? Infinity
potential 0.
Now if it was a negative charge, can anyone tell me what is the potential at point P?
Minus k q by.
If it is positive, it is plus kq by r. If it is negative charge, then it is minus kq by r. Clear? Everything clear? Done? Understood?
Yes, sir.
Now tell me, I will draw a graph also. You also draw that graph. Tell me how potential varies with R. How potential varies with R. How field varies with R. Tell me. QQ by R square. KQ by R square. So inversely proportional to R square. This is inversely proportional to R. Inversely proportional to R.
Just straight line decrease.
No.
Like 1 by R.
X. Okay, I go up. Okay, and inversely, if I go away from this charge, positive charge, the potential will continuously increase. Sorry, decrease, and decrease. Do you understand?
Yes.
Did you understand? This whole thing you understand? Did you write whole thing?
Yes.
This is a positive charge. This is a positive charge. The field will be radiated outwards. Here, done. So we understood potential. We understood potential is basically line integral of electric field. We understood potential to be a point charge, basically KQ by R, and we understood how it varies also. So we have heard about potential difference also. What is potential difference?
Difference in potential between the 2 points?
Simple. It is the difference between potential of 2 points. We have nothing else. Nothing else. If I say potential difference, did you write that previous one?
Yes.
Potential difference. Potential. Okay, before that, let me tell you one more concept. Potential difference later already defined. No, nothing. Just potential difference is the point. Now look here. If I have this 1 point charge, some r distance away, what is the potential? If I have point q charge, q point positive charge, how much is the electric field? KQ by r square. How much is the potential?
KQ by r.
If I have 2 points now, 2 point charge, what is the field here? 2 point charge. What is the field here?
Field where?
KQ by r square, KQ by r square. The vector sum.
Okay.
Yes or no? Yes or no? Simply do vector sum. With components do everything, it's easy. What if we have now 2 or 3 or 4 point charges and I need to find a potential at some point? See, this is called discrete set of charges. If I have charge Q1, if I have another charge, let's suppose Q2, if I have another set of charge called Q3. Now, at any point P, at any point basically, let's suppose this is at R1 distance away, this is R2 distance away, this is R3 distance away. If I wanted to find a field, it was easy. Field to this, vector sum, finish. Because field was a vector quantity. But potential, you are lucky that it's a scalar quantity. It is a scalar quantity. If I want to find potential at P, you know how will I find? Nothing. It's very easy. The net potential at P will be nothing but V1 plus V2 plus V3 and so on. Depends on number of charges. We have it.
Just direct sum.
Direct and direct and. Clear? Write this.
So what about potential difference?
Huh? Potential difference I will tell you later. Nothing this. Potential difference will be 2 points. I will show you some things I will show here.
So after this can we have the
Okay.
so we got points?
By the superimposition principle, the potential V at P, any point P, due to total charge configuration. Total charge configuration means n number of charges. It will be simply algebraic sum of potential due to individual charges. Because it is a scalar point. Hey, are you getting it? No need to worry about relation here. You just get it. Simple go add, kq by r, kq by r, kq by r, minus kq by r, plus kq by r. Only point is we should know the distance between them. Which test?
Keep it as maths and chemistry. Last time that physics and bio.
This time at scope we will complete the whole thing.
No, others.
But mostly we will complete it. I will try to.
Well, when is it?
Chemistry is on Wednesday, maths is on Tuesday.
Just in the tandem.
What?
Just in the tandem.
Yeah, this is.
Okay, when is the other thing?
Did you finish this? Did you finish this? Later on you will do. Write it fast, please. Done? Look here. Look here. What is there, man? Nothing. Okay. We need to find potential at C. We need to find potential at C. Sir? Why nothing? Because how many charges are there on the corners? Potential due to this direction, this direction. No. Hey, what direction, man? Potential. Only magnitude. Only magnitude. So whatever electric field was there, yes, then this will be repulsive. This will be also repulsive, right? Electric field I'm saying. Here it will be attractive, and here it will be repulsive. Add these two vectors. I'm talking about electric field. Here these two will directly add. Yes, we get some answer. Here there will be also repulsive force. Some electric field will go E1. You got some E2, E3. Just subtract these two, you will get one thing. For example, you got here. This is E. Then you got some answer here E2, right? Very easy. Then angle between them, find resultant. Resultant will be somewhere here. Okay, depends on what angle is it. If it's 90 degrees, so it's under root, simply root 2E. That is different way. That is different thing. Okay, different thing. Here potential at C. No need to worry about direction. Potential at C is V1 plus V2 plus V3 plus V4. How many charges we have? 4 charges. Due to one charge, let's suppose this is one. What is the potential? K cube by R. What is the potential here? 2K cube by same distance R, because distance will be same, right? R and R. Clear? Third, 3K cube by R. Last, minus K cube by R. This and this gets cancelled. 3 and 2, 5K cube by R. So what is this R? R is distance. R is distance. This is L. This is L. This is 90 degree. Do like this. 90 degree. This is L. This is L. How is total distance? Root 2L. Right? Total. Half of that is L by root 2. L by root 2. So this is L by root 2. L by root 2. L by root 2. L by. Hey, is it tough? Is it tough? This maths?
No, that's
Hey, if someone didn't understand, I will have to help. Huh? Pythagoras, fellow man. L. Base square, hypotenuse square. So this is root 2 L you will get. Divide by 2 because this is 2 parts. So L by 2, L by 2, L by under root 2, L by under root 2, L by under root 2. Done? Understood? Okay. Put the value there. Put the value here. So L under root 2. So it is 5 under root 2 K cube by L. This is the total potential at C. This is the total potential at C. If it is a square, how much will be this angle? 90? 90? Yes. I didn't make it perfect square, otherwise it will be 90. I made it like rectangular, so it's L. Can you do one thing at home? Can you find electric field at this point? At this point? See, I will tell you how. Very easy. Look here. Due to this, electric field will be K cube by R square. Yes or no? Due to this, K 2 cube by R square. Clear? Due to this, again this side on negative charge. Yes or no? Like this is negative charge. Negative charge field will be towards. Correct? So K cube. No, we show the direction of need to show.
Yeah.
K cube by R square. Add these two directly. So this will be 3K cube. 3K cube by R square. Will it be? Yes. So we get here 3K cube by R square. Okay, sir. Done. This one done. This one done also. Now left this one. Right? How much will be? 3kq by r square. Sir, solve this, you get 2kq by r square. Are you yes or no? Yes or no? Now, sir, 90 degree angle between them. Put this as some constant E, something. Okay. Now, angle, wherever the angle between two vectors is 90. What is the net field? E net will be under root of E1 square plus E2 square. Can you do it? Can you do it now? Can you do it now? Put E1, put E2, get whatever answer you want, you will get it.
KQ by r square root 13.
Try it home. Will you try? Will you try? Here we had to worry about direction because it was what? It was electric field. It was electric field. So what about force? If I put a charge Q0 here, for force I need to put a charge. Yes. Let's suppose I put a Q charge here. Can you find force also? Same thing, man. KQ1 Q2 by r square. Direction repulsive, direction repulsive, direction attractive, direction repulsive. Same like electric field. Find that also very easy. Whatever potential, sir. Potential is nothing. Direction this way potential, one potential, two potential. No, sir. So that. Are you getting now?
Yes.
Are you getting now?
Yes.
Is it done? Is it done? One homework. One homework. Last time homework also gave her, right? Second homework. This is our second homework. Nothing, man. This is Q1. This is Q2. This is Q3. Hello. Q1, Q2, Q3. This is Q1. This is Q2. This is Q3. Q1 is located at 0, A something. This is the point where we need to find potential, but it's potential at B, A. B, A. What is the distance here? B. What is the distance here? A. What is the distance here? A, B, right? Under root A square plus B square. Array, correct or not? So this is under root A square plus B square. So what is the potential here? Array, nothing, man. KQ1 by B square.